So what we've done so far in constraint satisfaction is we've looked at constraint satisfaction defined in terms of variables, domains, and constraints. And then we looked at 3 different algorithms for solving them. One is to search, to split on variables until you find a solution. The second one is arc consistency with domain splitting. Together, we can use those for solving constraints. And the third one we started last time was about local search. And what we're going to do today is we're going to keep talking about local search. Okay, does anyone have any questions about any of these? All right. So let's start off with a couple of clicker questions to make sure that we're all on the same page. So what is not true of arc consistency with domain splitting? A, arc consistency needs domain splitting to solve problems in general. B, together they can solve CSPs in polynomial time. C, they typically result in a smaller search space than using search without arc consistency. Or D, they always terminate with a solution if there is one for finite CSPs. So which of these is not true? Okay, does anyone need more time? Seem to have a few fewer people here. Anyone need more time? Oh, good. Oh. Oh, that's exciting. So let's talk about them. Arc consistency needs domain splitting. Arc consistency by itself doesn't solve the problem. Right, so it doesn't solve CSPs in general. So arc consistency needs domain splitting. Remember we had arc consistency which stopped and we hadn't actually solved the problem. We didn't know if there was a solution. So A is true. Let's do C. They typically result in a smaller search space, and using search without arc consistency. Arc consistency can be used to prune domains so that we don't repeatedly prune them in different parts of the search space. So C is also true. D, if there's a finite CSP, they always terminate. Right? There's only a finite number of variables to split, and there's only a finite number of sizes. But together they don't solve CSPs, so B is false. So B is the correct answer here. They don't solve it in polynomial time. In fact, we can't solve CSPs in general in polynomial time. So the answer here is B. Any questions about that? Yeah. Any questions about that? Okay. 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 So we started last time with local search. So here's a question we should know from last time. Which of the following is not true of local search? A, it maintains an assignment of value to each variable. B, after it is assigned a value, it should be, it does arc consistency to prune domains. C, it can run indefinitely if not terminated. Or D, it can sometimes find solutions quickly. So what's not true? All right, does anyone need more time? It doesn't move. Oh. The answer is B. All right. So what we're doing is we're maintaining a value for each assignment. So this is the slide that we started off last time. Let's go through to talk about this more. So here's the local search we did last time. We maintain this completive assignment of value to every variable. Okay, that's what we're going to do. We're going to assign a value to every variable that exists. And we're going to start either with a random assignment or a good guess. And we're just going to repeatedly select the variable and select a new value for it. Okay, so until we found a solution. So in this, so here it's a very simple step, is all we're doing is selecting a variable to change, and we're selecting a value to change it to. So what we're going to do is just choose a variable, change it. Choose a variable, change it. Right? Arc consistency makes no sense. It doesn't appear here at all. It makes no sense because you don't have any domains. We just have one assignment of a value to each variable. Okay, what did... hang on. Sometimes it can run indefinitely, and sometimes it can find solutions quickly, because we're just, essentially, if we just select a random value, if we just select a value, randomly assign it quickly, a good solution, we can find one quickly. All right. Any questions about that in that abstract sense? Okay. Whoops. So at the end of the day, what we're going to do is we're going to choose local search for just basic cases. Then we're going to compare local search algorithms with runtime distributions, and we're going to explain how randomization can help. And most of today, we're just going to effectively just play and see what we're going to play and see how we're going to go. All right. So is everyone clear about what's going on? Are there any questions about this basic algorithm? So let's do the first one that we did last time was local search, was greedy descent. We're going to select a variable that participates in the most conflict, and we're going to select a value for that variable that minimizes the number of conflicts. I'm going to keep going until we found a solution. So let's look at this. So what we're going to do to start this, the only choice we have is to initialize it. And in this domain here, the red arc, so A is not equal to D, A is equal to D is not satisfied, B is not equal to D is not satisfied, C is less than D is not satisfied. But the other one, so E is less than A is satisfied. So when we make a random assignment of a value to every variable, some of these constraints are satisfied and some are not satisfied, right? So now, what we're going to do is we're now going to, just to show what's happening here. So if we look at the algorithm options here, what we're going to do in this algorithm, I'm going to keep referring back to this. So in this algorithm, we're going to do two-stage. We're going to choose the best node 100% of the time. So we're always going to choose the best node, which is the node which is in the least, the node which participates in the most conflicts. And we're always going to choose the best value 100% of the time. So that's how we're going to read this. So which variables are going to pick? Which one participates in the most conflicts? D. Someone said, I think. Okay, so we're going to pick D. Which value can we do to make sure that we have which values can we choose to minimize the number of conflicts? Okay. So we could choose 3. What about, what did we do? We could do 3. If you do 3, 2. So in here you can actually play with, if you choose 1, there's 3 conflicts. If you change 2, there's 2 conflicts. If you change it to 3, then there's 1 conflict. If you change it to 4, we're not going to change it because we're going to change it. So if we now do D, we're going to step it. Okay, so we change it to D. Now we have 2 conflicts. Now we're going to choose C. And we're going to change it to 3. Why did it change to 3? Right, so it could either be, so it's either 1, 3, or 4, this variable. So if it's 4, there's 2 conflict. If it's 1, there's 1 conflict. If it's 3, then there's 1 conflict. So it's going to pick one of those 2 at random. And it picked 3. Right, so now it's going to pick Now there's two variables within conflict. It's going to pick one at random. It's going to pick C again. It's going to change it to 1. And now it's going to pick another one at random. It's going to pick C again. It's going to change it to 2. It's going to check C again. It's now going to change C. It's going to wander around for a while. And it's stuck. Maybe. Right, so this is actually stuck now. It's always picking the best thing. It's not, it can't find a solution, I think. So what we could do is we could initialize it again. Let's try another one. And now we can start stepping again. We're going to pick a variable, we're going to change it. Pick a variable, change it. And are we stuck again? Oh, it's stuck again. We're going to initialize it. We're going to step again. And we quickly found a solution. Does it make sense what we're trying to doing there? Just picking a variable, changing its value. We're checking the variable that looks best. We're going to change the value for it. Any questions about that? All right. So there's another algorithm. Which is we'll call any conflict. So we're going to, what we're going to do is start with a random assignment. We're going to select the variable at random from the variables that participate in conflicts. So we're not going to choose the variable that has the most conflicts. We're just going to choose a variable that participates in conflicts. And then we're going to select the value for that variable that minimizes the number of conflicts. We're going to keep doing that until we find a satisfying assignment. So if we do that with this one, so we're going to change hill options here. Oh. So instead of choosing the best node, we're going to choose this node, calls it a random red node. We're going to choose a random node so we're going to initialize it. And now we're going to step, we're just going to pick one of the variables at random and change it to its best value. And if we keep doing this, we'll find that it eventually stops. So if I initialize it again, every time you do it, it's different. If we play with it here, it stops here. Does that make sense what we're doing? Just picking a random variable that's red. Okay. A random variable that participates in a constraint. Okay. So is that clear what the algorithms are doing? That's sort of pretty important. It's clear what we do. All we're doing is picking a variable, picking a value, just changing it. If you think about it in terms of assigning courses to time slots, we've got assignment of a course to every time slot. We're just going to change time slots for courses. We're going to move courses around until we find a satisfying solution to courses for time slots. Here we're just having these variables that are in the abstract. Okay. Let's go here. And then we did this runtime distribution. We finished off doing this. We looked at, on x-axis, the runtime or the number of steps. On the y-axis is the proportion or the number of runs that are solved within that runtime. Okay, so we're plotting here. On the x-axis, we're plotting the time or the number of steps. In what we're going to do, we're always going to plot the number of steps. But in general, you want to do the time. We're going to talk about how we do times. And in the y-axis, it's either the proportion or the number of runs of what's going on. So let's go back to, so let's go back to here. So now we're going to choose this. This is now the greedy descent. And what we're going to do is do this batch run. And going to terminate after 1,000 steps. And we're going to do this funny graph. I'm going to put on log scale here. And so what this is now telling us, this is just one run. What we did is we ran it 100 times, the algorithm 100 times. We sorted the runs by run time, and that's on the y-axis. So within 2 steps, we'd solved 3 of the problems, and within 4 steps, it looks like we'd solved about 17 of the problems, and within 8 steps, we'd solved 35 of the 100 problems. Okay, is that clear what's showing there? So on the x-axis is just how many steps, and the y-axis is how many problems we'd solved in that time. If I run it again, the same algorithm, and it's going to run them all, then it's going to sort them. We'll find out that it looks pretty similar, and a lot of those ran over the right-hand side. Right, a lot of those algorithms that we saw ran over the right-hand side and didn't stop. So in fact, what proportion of them didn't stop? About, who can see what proportion didn't stop? About. So this point here, right? So these points here is around 60% of them didn't halt. So 60% of them halted. Right, the median run time was around 12 steps here. The median was about here. It was around 16 steps. Okay, does that make sense what this is showing? The 25th percentile, which would be down at 25 here, is around there. It's around 5 steps. So the 25th, you could solve 25%, about 25% of them within 5 steps. You could solve 50% of them within about 16 steps. And we can ask this for everything in between. Is that clear what this says? Any questions about this? Okay. And if you run it a few times, they actually tend to look similar. So one algorithm seems to have a very similar profile to other algorithms. When you average a whole lot of randomness together, you actually get regularity. So this is what people study in statistics. So now let's change the algorithm. So what we're going to do is, we're going to choose any conflicts. We're just going to look for variables that are in a conflict. And we're going to do another batch run. And what do you think is going to happen in here? So instead of choosing the best one, we're just going to choose any one in the conflict. What do you guess is going to happen here? Well, let's look at what happens. We run it. All right. Oh, that's an awful color. Let's run it again. So what tends to happen here is it does a few things that are interesting. It solves all of them. So if you look at the top right here, it solves all of the problems. So the fact that it goes up to there, to 100%, means it solved all the problems. The fact that this other one did look like this and stopped at around 60%, this means it solved 60% of the problems. Okay, then if you look at something down here, if you look at this 25% range is here. See, one of them solved it in 5, and the other ones took about 10 steps. So if you wanted to solve the problem 25% of the problems, then this algorithm is much faster than this algorithm. So this could solve 25% of them in 5 steps. This took 9 steps. Okay? So this took 5 steps, and this took 9 steps about. So this is the number of steps it takes to solve 25% of the problems. And if you look at the median, which has a better median, they're both looking pretty similar here. There's all a big mess around the median. So now we can sort of start looking at different algorithms, and they have different profiles on this. And what tends to happen is that algorithms that always solve them are often a lot slower for small problems than problems that can solve more of these. Yes?
What problems are you having? What does these problems refer to? Isn't that we only have one problem?
We have one problem, multiple runs on one problem. So we ran the problem. So each of these lines is running the problem 100 times. Exactly the same problem, but 100 times we ran it, and each time we ran it, we had a different number of steps. Right? And so this is the distribution of the number of steps to solve it, the same problem, we haven't changed the problem, for how many steps we're solving for the same problem. Right? So these are all the same problem, we're just changing the number, we're just running the algorithm a different number of times. Okay, any questions about that? Yes?
Increase the problem complexity with the increase the problem complexity with the lines far apart?
Yes. Well, as you increase the complexity of these problems, then they tend to take much, much more time. Yes, the value there can be a lot bigger. So when you get, these are pretty tiny problems, and the real problems, the constraint satisfaction problems for solving they're used for solving allocating courses, right? Has tens of thousands of variables, and we have a dozen. Yeah, so when you get bigger problems, this gets a lot more distinct. But it's hard for me to demo that. I just wanted to get exactly the same problem that we use for the CSPs of solving it here. So these are all toy, silly problems, and no one does it for this size problem. But it's the same principle that holds much bigger problems. Any other questions?
When would you need to solve like 0.5% of the problem?
So the question was, when do you care about solving 25? If I could solve a problem in 25% of the time, I can try a number of times. I can try it 10 times, and I'm very likely to solve it. Right? The probability that I fail to solve it 10 times is very low. It's 1 minus 0.75 to the 10th. Right? So if once I get a small probability to solve it, I can keep retrying it. Well, actually, we'll get to that in a minute. So keep that question in mind. Okay. Any questions about that so far? Okay. Oh, where am I? I'm here. Whoops. Okay. So what we can do is you can also do randomized steps as well. So we could actually think about, you could do a random restart of values. So instead of doing this algorithm a number of times, we could reselect values for all variables. We could do a random restart. And the other thing we could do is we could do a random walk. We can select variables and/or values at random. So we can start doing a random walk. And here a random walk means we could either select a variable from those that participate in conflicts, or we could select a variable from all of the variables. So we can actually do randomized walks instead of just optimizing things. And let's have a look. So what we could do in here is so let's do a different algorithm. So what we're going to do is, instead of choosing the best node 100% of the time, which we did before, remember we chose the best line. We didn't solve all the problems when we're solving it 100% of the time. Let's instead suppose that we can choose it 70% of the time. 70% of the time we're going to choose the best node, and 30% of the time we're going to choose a random node that participates in a conflict. So what do you think might happen? What do you think this curve will look like when I do this? A little. It'll finish all the time, yes? It'll take longer to finish. Is that what you predict? So let's run it. It's here. It's this one. Oh, close. Oh, you can't read that, can I? I can't read it. So what's happening here is it's picking colours at random. Let's run it again. That's a better colour. All right. So if you look at what's happening here, it's this darker green one. That's awful. I've got too many lines there now. So it's sort of doing a mix of these two algorithms, right? What it's doing is it's effectively going between these two algorithms. It's going better, for the lower numbers, it's doing better than the one that always picks a red node. But up here it's doing worse than that. Oh, actually let's clear it. Let's run these again. Let's do it again. And I'm going to do it. So let's do this again. Let's go back here. Oh no, algorithm options. We're going to choose the best node 100% of the time. We're going to do this again so we can see it. So this time I'm going to run it 1,000 times. Running it 1,000 times for a maximum of 1,000 means it's going to take longer, but the statistics, because we're averaging over 1,000 runs, not 100 runs, the statistics are going to be much more stable. You can be able to see what's going on better. And if you look at this, all right. Well, if you plot this a number of times, they're going to be very similar, these curves, whereas there's a lot more noise when you run it 100 times. So now let's run it this time, and hopefully we'll get it. Now we're going to pick 100% of the time, we're going to pick a random red node, which here means a random red node here, which means that we're going to just pick any conflict. So anything that's in a conflict, we're going to pick it at random. And we'll end up, it's always useful to run it a few times. I'll just run it twice. And they look really similar, the curves. Right? One of the things you should notice is when you run it 1,000 times, the curves look very similar to each other. Okay, now let's run this other one. Because I never know what's going to happen here, because every time I run it, it does something different. Okay, now we're going to run 70% of the time, we're going to run this. And 30% of the time, we're going to do that. And now we're going to do another batch run. And if you look at dark green things, we'll find that at small numbers, it actually looks, let's run it again. Because you want to make sure that it's not just a statistical irregularity, right? Just by random chance things go wrong. But you'll find that it's pretty stable. So this algorithm here, at small numbers, it actually runs, at small values here, it actually runs just as fast as the algorithm as just always choosing, right, the best one. Right, so in fact, this other one, this 70% one, actually looks a bit like that. Right, so for low levels, it actually works nearly as well, but for higher levels, it doesn't work quite as well as this other algorithm. And this is telling us going on here? So when we select it, 70% of the time we're going to select this, the best one. Right, so 70% of the time we're going to select the best node, and 30% of the time we're just going to select any node. Right, so this was 30%, so this was 70% the best, and 30% a random conflict node. Okay, and we can see here what it's dominant. So essentially it dominates this other algorithm. Right, if you try and look at what it differs in here, one algorithm here is going to dominate another if it's always above. Right? So let's look at another algorithm. What happens if instead of picking the best everything, so instead of picking the best value, let's suppose we just pick the best value 50% of the time, and the other 50% of the time we pick a random value. What do you think is going to happen? So we're picking the best node 70% of the time, we're picking a random node, but we're only 50% of the time we're picking the best value we can. The other time we're going to pick one at random. How do you think this might work? Is this a better algorithm than the other one? Well, adding randomness before helped us, right? Adding randomness before helped because instead of going from 100% of the best node to 70% of the best node, we actually went better. Right, so this one, the 70% worked better than 60%, worked better than the one that was 100%. So if we run this, and it's, you can sort of tell. So what it's doing is running all these, then it's going to sort them. Once you get out there, it's going to sort them. We're going to find out this one here works much worse. So this is dominated by the other one. So choosing the best value only 50% of the time is worse. It doesn't help us. And we can see that from this graph. Can anyone guess why this 70% best is worse at the high number of steps than the one that just chooses any conflict? Yeah, so this one here is more likely. So these are the ones that it starts off close to the solution and it can find a solution quickly. These are the problems for which it starts a long way from the problem and it's effectively walking around the wrong part of the space. It's doing a lot. It's got to walk randomly. It's got to do much more randomness to get out of this local minimum. Is what's going on here. So randomness helps us get out of these things which are called local minima. Because I think it's clear what this is showing us. So is it clear what this graph's showing us? Any questions about it? Yes.
The question if you have a different problem, similar class of problems, but a different problem in the way it's designed. So the graphs will be similar for the same values as here, or will the graphs be completely different?
So it depends on, well, let's do that. So that was when we did there was the first scheduling problem for which arc consistency was very efficient for it. We'll do the other one, which arc consistency, this one here. This is the other problem. And I think if I try, what are the options? Let's try back it to 100%. And we're going to choose the best node 100% of the time. And if we do a batch run on this, we'll find that it can solve about 89%, or it can solve a much higher proportion of the solutions in 1,000 steps. The other one's about 60%. This is about, about 85% of them. Because this is actually an easier problem, there are two solutions here instead of one. So as this number of solutions goes up, it's actually easy to find solutions. If I then do, let's do all three again. Let's do 0, 100, and we'll do another batch run. And this is now doing a random red node. It's going to look, in some sense, similar to the other one. And let's just do one more run of this one. Algorithm options, we'll do 70% best. Okay. And we'll do another batch run on this. And we'll find that it's pretty similar, except we can't read green again. Right, so this is qualitatively similar than these ones. They all look a bit like this. The greedy ones, the ones that always pick the best one, tend to stop after a while. The one on the right is an easier problem, has more solutions than the one on the left. The one on the left only has one solution, the one on the right actually has two solutions. As you get more and more solutions, it goes more. It stops doing randomized walks, doing 70% walk here, solve this problem. Right, so the 70% walk solved similar to the lower numbers here and similar to this upper value here. So they're similar. Okay. Let's do one more thing. So one of the things we didn't try was a random restart. And the question that we got here was, what good is an algorithm that can solve 25% of the times? So let's try and look at what happens there. Let's go back to this one, which is load sample CSP. I'm going to load scheduling problem 1 again. So we did it 25% of the times. It could solve, how many problems was that? About 6 or 7. And it sort of at this time, at around 10 steps, it could solve 40% of the problems. So let's suppose instead of when we get to 9 steps, let's suppose instead of doing it, we just give up and start again. Right, so we have something that can solve 30% of the problems fast, but is not very good. So what happens if we do an algorithm that does 100% the best run? Remember, that wasn't very good before. What we're going to do is, we're going to restart at every, 9 steps, 10 steps? 9 steps. We're going to choose 100% of the time the best one. And we're going to choose 100% of the time the best value. We're going to keep restarting it after every 9 steps. What's this going to do? What do you think this will do? What's it going to do? Well, let's see. Oh. I didn't do it on top of the other one. Oh, well. Let's batch run that again. But I lost the other ones. Let's do it again. This is with the random restart. Let's compare it to the non-random restart. Algorithm options. Non-random restart. We're not going to random restart. We'll do it every 1,000,000 steps. And we'll do this. So turns out the logarithm scale is a nice thing to look at. So this is the non-random restart, and it's going to, after 9 steps, It's going to act similar to the first 9 steps, and then it's going to give up. The other one's going to keep retrying. And let's try it compared to best node is and it's going to do a batch run. And this is now the random red node. So now it's doing just picking any random node, and we'll see that it's the bottom one here is actually worse than this other keeping doing a random restart. Random restart actually works quite well for this. It's got a funny shape to it. It goes up after 9, and after 9 it keeps, because the first few steps it doesn't help it, but after a while it either finds a solution quickly or it doesn't find a solution. Okay? So the second assignment, one of the questions is play with this and tell us what you find, right? Because what happens is it really depends on what algorithms we're doing. What tends to happen is that greedy tends to not very good, random tends to be not very good, but a mix of them turns out to work very well. And that's what we're going to keep finding, right? So random and mix of random and greedy tends to work well. Okay, let's go to here. And let's try and see if we can understand why. Let's look at this. So now what we're going to try and do is we're going to try and find a minimum value. So we're going to look at 2 different things, 2 different ideas, one of which is a greedy descent. We're going to start from some position and we're going to keep moving downhill. So we're going to try and keep iteratively improving our solution until we find it. And otherwise we're going to pick values at random and report the minimum value found. And the question is, which one do you work to find, which is better to find this global minimum? And if you want your intuition to work, it's really hard in these problems because they have millions of dimensions. They're very simple problems with millions of dimensions. We can actually look at it in sort of simpler problems. So let's look at 2 one-dimensional search spaces, and we can either step right or left a small amount of time. So a greedy descent means we're going to go downhill, and a random restart means we're going to do a random restart. And so we can either do random restarts and downhill, or we could do a greedy, or we could do a randomized walk, right? We do a random walk. So what would tend to happen, so we're going to pick a value at random, and in A we can either do a random walk, so some of the time we're going to mostly try and move downhill, but sometimes we can do a random step. So if you look at this one on the left, what's going to happen there with a greedy walk mixed with, essentially we're going to go downhill, but sometimes we can do a random step outwards. So what's going to happen in the left one? People imagine what's going on. It's hard to imagine these problems like the CSPs with thousands of dimensions. So this is sort of a slightly different problem, but hopefully you can visualize what's going on. So we're going to look at greedy descent with random walk. So some of the time we're going to do greedy descent, some of the times we can do random walk. And greedy descent means downhill in this slope. And random walk means we're going to do some steps at random. Right? So most of the time there's a probabilistic mix of you go downhill, otherwise you step randomly. What would tend to happen in this left-hand one with this algorithm? So in this left-hand one here, what where does downhill get to us? If we start at the left-hand thing, right? Can you imagine instead of stepping there and occasionally you pick random steps? We're going to go downhill except we're going to step randomly. So in this left-hand one, we tend to get stuck in these local minima, right? We tend to get stuck. It takes a lot of random walking to get out of that left hand. So if we're in this position here, if you're in this point here, it takes a lot of random steps to get out of here. Right? So in the left-hand graph here, this algorithm tends to get stuck into local minima. Right? This one here, this one tends to get stuck into local minima. This one gets stuck in local minima. Once it's in this point, it can't get out of it. It takes a lot of random walks and keeps falling down again. Right, so this gets stuck in local minima. What about the one on the right? Well, if you're in one of these local minima, it doesn't take very many random steps to get out of it. Right, so for this one here on the right, this algorithm tends to escape those local minima. The local minima take a very few steps to get out of them. Okay, so for this one here, it tends to work well. So for this one here, for a graph that looks like this, right? When we're in one of these points, when we're in one of these local minima, it takes very few steps to get out of it. And so this one here this algorithm tends to work really well on the graphs that look like this. Now try and imagine it in a million dimensions, and you can't, but that's fine. But this is sort of essentially what happens. If there's some of these you can escape with a few random walks, you can escape the local minima, but some of them you can't. What about a random restart? So you do a random restart with a greedy descent. Greedy descent with occasional random restart. What happens to one on the left? What happens here? So it tends to find. So what happens is all we need to do is once we're in this center of attraction in the middle, this valley here, a walk will get us their solution. Right? So in this one, right, so as soon as we're in this area, we can solve the problem. So we tend to solve the problem quickly. With this one, works well. So here, as soon as we get here, we get back to here. If we get here, we get to here, but by random chance, some of the times we're going to end up in this global area. Whereas this one here on the right, so this one here, it works well. But if you have this funny graph like this, right, to not get stuck in one of these local minima is very unusual. Okay, so it's hard to imagine, so you can sort of, hopefully that's useful way to imagine what's going on, but that's what happens in these things. So sometimes you get these local minima that you get stuck in, and you can't escape by random walking. And some of the times you get these sort of local minima that you can escape with local walking. And you can play with these, yes.
But you have to have enough steps to get to the minimum.
Yes.
To start before getting to the minimum, you have to be like 10 steps. Have 10 steps from the minimum to get.
Yes. That's right. But these algorithms actually do lots and lots of steps to do these things. I mean, we had a small problem with a small number of steps. But these steps are really fast. You can do millions of steps in a second, right? These things are very fast because it's sort of almost trivial algorithms to implement. You can do lots of steps, and so you can find these ones as well. Okay, let's stop there. But these are fast algorithms. They're fun to do. All right, have a good Thanksgiving.